ScienceHelpNow.com. This is Topic 6, Work, Energy, and Power. In Section 6.3, I'll be talking about the work done when the force is at an angle to the displacement. Now, of course, that's an angle other than 0 degrees, 90 degrees, or 180 degrees. As we discussed in the previous two videos in this topic, 0 or 180 degrees means that the force is parallel to the displacement. 90 degrees means that the force is perpendicular to the displacement, and we've discussed those situations already. So here we go with forces that are at an angle to the displacement. When is work done in physics? In previous videos, we've said that when the force and displacement are parallel to each other, work is simply the product of the force and displacement. You simply multiply the force times the displacement. Now, when the force and displacement are perpendicular, or if there is no displacement, then no work is done. The work is equal to 0 joules. Now, in this video, we will be focusing on when the force is at an angle to the displacement. What you have to do, you must calculate the component of the force that is parallel to the displacement. This component does work. You'll be multiplying this component of the force by the displacement to calculate the work. All right, so a quick little review of things that we covered in videos 1 and 2 of this topic. Review example number 1, when a force and displacement are parallel. Right, so we've got a 15 Newton force to the right and a 2 meter displacement also to the right. Now you notice they're both to the right, so they are parallel, so the angle between those two vectors is 0 degrees. Right, all you have to do is multiply the force by the displacement. So the work done is going to be equal to the force times the displacement. Keep in mind that that entire force is parallel to the displacement. All right, so we have here 15 newtons times 2 meters. All right, so the work done is 30 Newton meters. Now, a Newton meter is a joule, so it's 30 joules. Now, both the 15 newtons and the 2 meters are in the same direction, so this work is positive. If, for example, we were looking at the friction, right, if we wanted to calculate the work, if there was a friction force here, right, of negative 15 newtons, if that were the case, and we were to multiply that force by the displacement, then that would be negative 15 newtons, and it would be negative work. All right, and while we're at it, the angle between the friction and the displacement, all right, opposite directions, this would be a 180 degree angle between the friction and the displacement. All right, opposite directions, 180 degrees, same direction, 0 degrees. All right, so this is what happens, this is how you calculate the work when you have parallel vectors. All right, these two are parallel, these two are parallel, same direction, the work is positive. Opposite directions, the work will come out negative. In our second review example, a force and displacement are perpendicular to each other. We have a 20 Newton applied force holding a book up. And the person is moving to the right, so the displacement is to the right. So the force holding the book up is in the upward direction, the displacement is to the right. What we find here is that no work is done. All right, the angle between the applied force and the displacement is a 90 degree angle. So they are perpendicular to each other. All right, and because the force and the displacement are perpendicular to each other, no work is done. So the work is 0 joules. Okay, and again, this is a 90-degree angle. Theta here is 90 degrees. So here is our first problem, where the force is at an angle to the displacement. Now that's an angle other than 0 or 180, which would mean parallel, or 90 degrees, which would be perpendicular. So the force and displacement are at an angle to each other, right, other than these three angles. Here we go. A 27.71 Newton force is applied at a 30-degree angle to the ground and towards the right. The object is displaced 4 meters to the right. All right, so let's draw a quick little diagram. Now, we're not going to draw any of the forces other than the force that we're talking about. We're talking about this force right here, the applied force. And we want to calculate the work done. All right, the problem is to calculate the work done by this force. All right, so here's the ground. All right, we've got some kind of an object. All right, and the force is at an angle to the ground. All right, at an angle to the displacement. All right, the displacement is to the right. The force is at an angle to the displacement. So this applied force here, force applied, 27.71 newtons. You'll see why they picked that number, all right, in just a minute. Now, the displacement, 4 meters to the right. All right, here's the displacement. D equals 4 meters to the right. All right, now, in physics, whenever you see an angle, you are probably going to have to calculate components of that vector, right? In this case, the force. So here is the horizontal component, right? Here's the vertical component. Now, we don't need the vertical component, all right? We want to figure out the work done by this force in this, as far as this displacement is concerned. So the component that we need is this horizontal component. We don't need the vertical component in this case. Let's get rid of him. So we're trying to calculate that, all right? So let's do the math. All right, I can get rid of this now. Let's calculate the component of this force that is parallel to the displacement. All right, right here. Now we know that this is a 30-degree angle. We were told that this is a 30-degree angle. All right. So, all right, cosine theta equals adjacent over hypotenuse. All right, adjacent over hypotenuse. All right, so if we want to find the adjacent, we're going to cross multiply, put this over 1. Right, the adjacent is going to be equal to the hypotenuse times the cosine of theta. The hypotenuse is 27.71 newtons. Cosine, 30 degrees. All right, so let's do that math. All right, the cosine of 30 is 0.866. Cosine of 30 comes out to 0.866. We're going to multiply that by 27.71. All right, and we're getting that the adjacent is 23.997 newtons. As far as I'm concerned, that's going to be 24, okay? So the adjacent is 24 newtons. All right, we'll go with that. All right, this adjacent right here, all right, all right, FA parallel, all right, is 24 newtons. Okay? So, what do we do next to calculate the work? So, what we have here is the component of this force that is parallel to the displacement. So to calculate work, we're going to take the component of the force that is parallel and multiply it by the displacement. All right, so work is going to be the component of the force that is parallel to the displacement times the displacement. All right, the component here that is parallel, right, is 24.0 newtons the displacement is 4 meters. All right, 24 times 4, all right, 80, 96. Don't need the calculator for that. All right, so we've got 96.0 joules. Newton meter is a joule. Okay, so this was just our first example of how to calculate the work done by a force that is at an angle to the displacement, an angle other than 0, 90, or 180 degrees. All right, what you do is you calculate the component of the force that is parallel to the displacement. All right, in this case, it's the adjacent. All right, so you're going to use cosine. All right, and then you take that component, the parallel component, and multiply it by the displacement. Quick little summary. When a force is at an angle to the displacement, that would be an angle other than 0, 90, or 180 degrees, only the component of the force, which is, what are you going to fill in there? Only the component of the force, which is blank, to the displacement. If you guessed parallel, you are right. Only the component of the force which is parallel to the displacement does what? Good. Does work. So, you need to calculate the parallel component. Now, for a flat surface, usually that's going to be x or the horizontal. All right? You need to calculate the parallel component of the force. All right? And again, usually the parallel component, if it's a flat surface, usually the parallel component is x or horizontal, usually determined using cosine. Not always, usually. You have to look at the diagram that you've drawn. You have to draw accurate diagrams, and you have to look at the diagram to decide whether to use cosine or sine. All right, another problem where the force is at an angle to the displacement. A man pulls a 4-kilogram box. Right, here's the box. 7 meters to the right. Here's the displacement, 7 meters to the right. With a rope at a 30-degree angle to the flat ground. So here's your 30-degree angle right here. Right, 30 degrees. At a 30-degree angle to the flat ground and a tension of 50 newtons. So the applied force here, he's pulling the rope with applied force of 50 newtons, which creates a tension in the rope of 50 newtons. Calculate the work done by the tension force in the rope. All right, now the only displacement is to the right, so the work done would be to the right. Right? Work is not a vector, let me not say it that way. But the only displacement is to the right, so the work done would have to be by the component of this force, which is to the right. All right, so let's calculate the parallel component of this force. All right, so this would be the parallel component of this force, or the horizontal component. The vertical component is here. We don't need that, so let's not worry about the vertical component. All right, we need the parallel component here. All right, I'll call that FA parallel. All right. So this is adjacent to this hypotenuse. So you're going to use cosine to calculate this parallel component of the force. All right, so let's get rid of this and start doing some of our calculations. Don't need this anymore. All right, so the cosine of theta is the adjacent over the hypotenuse. The adjacent here is what we want, FA parallel. All right, the hypotenuse is the applied force or the tension there in the rope. All right, let's get A by itself, cross multiply. All right, A equals H cosine theta. All right, so the hypotenuse is 50 newtons, cosine 30 degrees. All right, let's do the math here. All right, 0.866 times 50, we've got 43.3 newtons. So the adjacent is 43.3 newtons. All right, right here, all right, FA parallel is 43.3 newtons. Okay, now, to calculate the work done by this force, all right, the only component that is doing work, right, is this component. So what we're going to do is multiply this component times the displacement. All right, I'll pause if necessary, get this copy down, do that work. All right, here we go. All right, so the work is equal to the force that is parallel to the displacement times the displacement. The force, the component of the force that is parallel is 43.3 newtons. The displacement is 7 meters. All right, let's do that multiplication. 43.3 times 7, 303.1 joules. All right, so this force does 303.1 joules of work. Only the component of this force that is parallel to the displacement participates in the work that is being done. In this problem, we've simply changed the angle. Instead of a 30-degree angle, we have a 60-degree angle. So let's just take a quick look at the problem again. The same man pulls a 4-kilogram box 7 meters to the right with an applied force of 50 newtons on a rope at a 60-degree angle to the flat ground. Calculate the work done by the applied force or the tension in the rope. All right, so again, the only component of this force that is doing work is the component that is parallel to the displacement. All right, here's the parallel component. Here's the perpendicular component. Remember, you can take any force, any vector actually, and break it up into components, as long as it starts and ends in the same place. Start, end. So this is a parallel component. This is a perpendicular component. Parallel and perpendicular to what? To the ground, or more importantly, to the displacement. So the only component that we need is this component, the parallel component, right? The component that is parallel to the displacement. We don't need this one. So we're not going to need sine. We're going to need to use cosine to calculate this component, because this component is adjacent to this angle. All right, so we use cosine. And here we go. Let's erase this. Don't need that anymore. And here we go. All right, so cosine theta equals the adjacent over the hypotenuse. Here's the adjacent, right? Here's the hypotenuse, right? Your right triangle is basically there. That's your right triangle. Here's the adjacent, here's the hypotenuse. Okay, cross multiply. All right, A times 1 equals H cosine theta. All right, H, the hypotenuse, is 50 newtons. Cosine of 60 degrees. Now probably most of you know that the cosine of 60 is a half. All right, I'll prove it to you here. Cosine 60, all right, is 0.5. I know you can't see that. You got to take my word for it. All right, so 50 times 0.5, all right, means that the adjacent is 25 newtons. Now notice that this adjacent at a 60-degree angle is much smaller than the adjacent was at the 30-degree angle in the previous problem. So this is a smaller force pulling this displacement of 7 meters, right? Pulling the box, a displacement of 7 meters. All right, so now let's calculate the work done by this force at the greater angle. I guess you imagine it's going to be less. All right, so here we go. How much work is done if you're pulling the box at this angle as opposed to the last problem where you were pulling the box at a much lower angle? All right, here we go. So the work is equal to the parallel component of the force, the component of the force parallel to the displacement, times the displacement. The parallel component is 25.0 newtons. We just calculated that. Times 7 meters. All right, 25 times 7, all right, 175, okay? You can do that in your head. All right, if you use your calculator if you have to, all right? 175, all right, we'll put a 0.0 there. Not really. Nope. 3 significant figures, 3 significant figures. All right, joules, okay? 175 joules. All right, so when we were pulling the box at the lower angle, the parallel component of the force was greater. So for the same 7 meter displacement, we did approximately 300 joules of work. At the higher angle, right, where the parallel component is much less, that lower parallel component times the same 7 meter displacement, you're doing less work. All right? Just a quick look at what happens to the parallel component as the angle increases from 0 to 90 degrees. Now keep in mind, this is a very specific situation. We're talking about the parallel component to a displacement to the right on a flat surface. All right? In other situations, you're going to have to draw a diagram and look at what's happening and analyze it by thinking, right, about what's happening compared to the drawing that you made. But here we go. All right, so when the angle is 0 degrees, let's say this is the displacement to the right, right? If the angle of the force is 0 degrees, same direction, look at how long, look at the magnitude of that parallel component. Now remember, these are all the same magnitude. All right, now, if we go to approximately a 20-degree angle here, right, look at the fact that the parallel component is now shorter. It only comes up to about here. Right? So as you're starting to increase the angle, the parallel component is starting to get shorter. How about this? Maybe this is a 40-degree angle. All right? The parallel component would come out to about here. Right? The parallel component, as the angle is increasing, the parallel component of that angle, of that force is decreasing. All right? Here, maybe that's a 50-degree angle. All right? So the parallel component now only comes to here. Right? There's your parallel. The parallel component got shorter again. All right, let's try this one. This is maybe an 80 or 75, 80-degree angle here. All right, look at the parallel component. Stops right there. Boom. Right? The parallel component is getting smaller and smaller and smaller. As the angle is increasing, the parallel component is getting smaller and smaller and smaller. For a 90-degree angle, the parallel component is 0. There is no parallel component. There is no component of this vector that is parallel to that displacement. All right? You see what's happening? Now, you could also, I don't want to get too messy here, but you could also look at what's happening to the perpendicular or vertical component. All right, here, the vertical component is 0. Now, look at the vertical component here. Look at the vertical component here. Look at the vertical component here. All right, as the angle is increasing, the vertical components are increasing. All right, and here's your completely vertical component. All right, so what happens to the parallel component as the angle increases from 0 to 90 degrees? All right, as the angle increases from 0 to 90 degrees, comma, the parallel component decreases. And again, we're specifically talking about the parallel component of the force relative to the displacement. Let's look at a practical application of angled forces. When trying to push or pull an object along flat ground, should you use a low angle, like 0 degrees, or a higher angle, and why? Well, if you're trying to push this box to the right, and you use a 0 degree angle, right, parallel to the displacement, all of your force, whatever force you apply here, is 100% contributing to the work that you're doing, pushing the box in that direction. Now, as soon as you start to put an angle onto your push, if you push like this, right, up, if you push like that, or if you push down like that, then some, here in this case pushing up, some of your force is picking the box up off the floor, which you probably don't want to do. In this case, if you're pushing down, then some of your force is digging the box down into the ground, which you don't want to do. So if you have any kind of an angle, the more angle you put on your pushing force, the less the component of your pushing force that's pushing the box in the direction you want it to go. So if at all possible, when you're trying to push a box to the right, bend your knees, don't use your back, bend your knees and get down low and push straight in the direction that you want the box to go. Take a look at this horse pulling this carriage. Notice that one of the best ways to attach the horse to the carriage is with a straight pull like this. Because that means that all of the horse's effort in pulling is going that way, the way that we're trying to go. The displacement is down the road. Now, assuming this is a flat road, this is the best way to attach the horse to the carriage. The more that this harness is at any kind of an angle, the smaller the parallel component of the horse's force. All right, so this is a good way to attach the horse to the carriage so that all of the horse's force is parallel to the direction that you're trying to go, to your displacement. So ultimately, the horse doesn't have to do as much work because he's not lifting the carriage up off the ground. Everything, all of the force that the horse puts in, pulls the carriage in that direction.